So a median is one of those segments that cuts across a triangle, specifically going from a vertex to the midpoint. And if you do that to all three sides, or from all three angles, the three medians of a triangle intersect at a single point of concurrency called the centroid. In this case, well, I'll get to this part in a second. First, it says list the median, so let's make sure we recognize that this time it is a consistent segment all the way from the vertex through the centroid to the midpoint. So for instance, AE would be one example, from the vertex all the way through the centroid, straight through to the other midpoint of the side. This should be marked as congruent there, BF. And then this one's C all the way to D, so CD. And when those three medians are drawn, they meet at a single point of concurrency, a special center that we call the centroid. And the centroid has two features to it. The way this is phrased suggests that it's the median that actually has the interesting elements, but of course it's the centroid that does this. So what happens is this median gets split such that whatever length the part going to the midpoint is, the part going to the vertex will be exactly twice that amount. In other words, the centroid cuts it in thirds, leaving a 2/3 chunk and a 1/3 chunk. So we could say, for example, the length BP will be twice the length BF, 2 times PF. Or we could say that PF is 1/3 the whole length of the median, which would be BF. Or we could say that the longer part, BP, is equal to 2/3 of the whole length. Now this last piece, I'm going to add on the kind of special attribute about it. And this is that this particular point is the center of gravity, or balance. So if you wanted to, for instance, spin this triangle on a finger, that would be the point that you'd want to put right on top of your finger, on top of a pen tip, and you should be able to then spin it based on that. Any questions on what a centroid is? Okay. So now we're going to do some application of what we can find from the centroid. And remember, like I talked about last class, there's the hypothesis component and there's the conclusion component. The hypothesis is that we have to connect the parts to make the centroid, which means if you go vertex to midpoint, vertex to midpoint, vertex to midpoint, creating a centroid, then it is split into this 1:2 ratio. So the hypothesis says that if I know this is the centroid, then from, for example, K to J, if L goes through that centroid to hit M, what point is M? What special value does that have?
Midpoint.
Good. It has to be the midpoint. It's part of the hypothesis. Therefore, if I know, as this suggests, that JK is equal to 22, then KM would be how big? Well, it's being bisected, so that means cut directly in half. So 22 over 2 would equal 11. KM is equal to 11. And then they tell us that KN, let's see the different color, KN is equal to 13. What do we know must be true based on that?
that NL is also equal to 13.
Good, because that has to be a midpoint, so those two parts must be the same. So NL has to be 13. And what can we then say about KL? Well, it's got to be the sum of those, 26. And lastly, they're telling us that OL is 18. So we know that JO similarly must be 18. And that the whole side length is double that, or 36. And again, this is all really the hypothesis, right? This is saying, in order to make this a centroid, these have to be midpoints, and these are features of midpointed sides. Any questions on that? Okay, now we're working into the conclusion side. So we're going to say Z is the centroid, and they're telling us TZ is equal to 60. So what can we surmise from that? Two things. Remember the little 2x and x relationship? If TZ is equal to 60, how long is ZY?
30.
Yeah, 30. And if we know that's 60 and that's 30, then how long is TY? Just add them up as 90. And then we know that XZ is 28. So how long must ZV be?
$56.
Good. 28 times 2 is equal to 56. So this part is 56. ZV, 56. And that means that XV, the whole length, would be the sum of those, 70, 84. And lastly, they tell us that WZ is 25. So what do we get to conclude from that?
ZU equals 50.
Easy peasy. Any questions on that? Okay. So the last center for us comes about when you take the three altitudes from the sides. Then you'll remember that altitude is when you're saying, how high up in the air am I? What's my height? And if you were on a mountaintop, that would not be measured by going down one sloped side or one less sloped side and measuring that whole length. Instead, it's as if you want to drop a string with a rock on it and find out how far that falls straight down with gravity, making a line perpendicular to the base. So an altitude is a segment joining a vertex to the opposite side so that it is perpendicular to that side. And in different triangles, that might look different. This is a traditional acute triangle. What we'd find is that the altitude drops through the middle-ish, right, in the interior, at least, of the triangle, as we'd expect. But here's an interesting one. This is an obtuse triangle. And what we can see is that at least for this vertex, to find its altitude, it's actually going to be an altitude on the outside. It's on the exterior of the triangle itself to measure how high up in the air that is. And then it's possible that it's a right triangle, in which case, at least for two of the vertices, that altitude is actually on the triangle legs itself. When I take the three altitudes of a triangle, they intersect at a point called the orthocenter, which is our fourth and final center. And unfortunately, the orthocenter is the middle stepchild of the family, kind of gets ignored. There's nothing really going on there. No benefits of the young kids, no additional responsibilities of the older kids. There is nothing, well, it's not that there's nothing special about it. It's one of the points in the 9-point circle and it falls on the Euler line, but those are well beyond a high school geometry course. So for your needs, you can say there's nothing special about Orthocenter. It is constructed from altitudes, AE, BF, and CD. And the Orthocenter would be a point. In this case, it's denoted as P, so we'll call it point P. So we've got 4 centers here, each constructed from 4 different types of segments and having different attributes as a result of that. This next page is a little kind of formative assessment to see if you understand this. So would you please do questions 1 through 5 up here yourself? Fill in those blanks, please. The circumcenter is created by the intersection of 3 whats?
Would that be perpendicular bisectors?
Yes, it would. Thank you. Okay, Bodhi is now out of it for the rest of the round. Thank you for your answer, Bodhi. The incenter is created by the intersection of 3 whats?
Angle bisectors.
Yes, and Brian is out. Angle bisectors. And the centroid is created by the intersection of 3
medians.
Nice pen. Medians. Whereas the orthocenter is created by the intersection of 3
Altitudes.
15. And now we're into the more kind of application side. A blank is equidistant from the vertices of a triangle.
Circumcenter.
Good. Circumcenter. Thank you, Jared. And lastly, a blank is equidistant from the sides of the triangle.
In center.
In center. Okay. Now, I think these give people problems. But this is the way it's going to be represented. So we're going to go through this kind of carefully. For each of these, you're going to determine whether it's a circumcenter, an incenter, a centroid, or an orthocenter. In order to do that, you should need to know whether they're perpendicular bisectors, angle bisectors, altitudes, or medians. What do you see in this picture?
Angle bisectors.
Agreed. If those are angle bisectors, then we know that their intersection forms what? The incenter. And that would then tell us that this would make one of those cool little circles just on the inside with that as a center, because it's equidistant from all the sides. Okay, what about number 2? What are those segments? I'm going to pause here for a second, because I think what we're discovering is that we need a level of understanding about these things that we haven't really summarized yet. So I'm sorry, but for those of you that are doing this on Google, this might be hard for you. And maybe what you do is you wait until we're finished and then you take a screenshot of this. But I'm going to fill in a chart here with you. So the first thing is we want to list all the types of segments. Perpendicular bisectors, and then we want angle bisectors, and then we want medians, and then we want altitudes. I'm probably going to mess with a lot of your organizational structures with this in a minute, but what I want to do is I want to go with first, I want features about these perpendicular bisectors. And this is where it's going to mess with people because I'm going to write the actual category headers on the bottom here. But the first question is it perpendicular to a side? Next question is, does it go through the midpoint of a side? Next question is, does it go through the vertex? Perpendicular, midpoint, vertex. And the last one is it an angle bisector? So when I'm talking about the perpendicular bisectors, what that means is it goes from a midpoint of the side, that's where it starts, and then it goes up perpendicular to that. It doesn't necessarily go through the vertex, and it doesn't necessarily bisect the angle, so I'm leaving those blank. An angle bisector, on the other hand, starts at the vertex and shoots out as an angle bisector. Whereas the medians start at the vertex and shoot across directly towards the midpoint of the opposite side. While the altitudes are measuring the height of the vertex as it runs down perpendicular to the side. And this last column is the center name. When we do the perpendicular bisectors, that makes the circumcenter. When we do the angle bisectors, that makes the incenter. The medians, that makes the centroid. And when we do the altitudes, that makes the orthocenter. I think this chart would be very helpful if you don't have the ability to create it yourself on your side. Hold on, let me just zoom in a little bit. I might suggest you video or you take a screen capture of that. And now, when we look at this thing, what we ask ourselves is, what evidence do I see there? Well, that little mark down there means it's perpendicular. So now I know it's either an altitude or a perpendicular bisector. If it's a perpendicular bisector, I also expect to see it go through the midpoint of the side. Do I have any evidence that goes through a midpoint here? No. But if it's perpendicular and it goes through the vertex, here it's perpendicular, it's going up through the vertex. Ah, perpendicular through the vertex. Yep, they're all doing that. Therefore, this is formed from 3 altitudes, constructing the orthocenter. Does that help a little bit? Okay, what do we got here? These are midpoints, and we're connecting midpoints to the vertex. So over here, we've got midpoints and vertex, looks like purple. So that's medians creating a centroid. All right, what about number 4?
perpendicular bisectors.
Excellent, because you see the perpendicular and you see the midpoint suggesting they're bisectors. But that only takes us halfway there. That produces what type of center?
Circumcenter.
Okay, let's leave 5 alone for a second. What about 6? These are midpoints. So the question is, are they going through the vertex or are they going perpendicular? If they don't appear perpendicular, it does look like they're going up to the vertex. Therefore, it's medians forming a centroid. Okay, again, I'm jumping around purposefully here. What about number 8? What do we see there?
Looks like altitudes.
I would agree. It does look like altitudes because they're perpendicular and through the vertex, which means this must be the orthocenter. Okay, we'll do number 9 next. What are those things?
Angle bisectors.
Which means the center formed is the
Incenter.
Yep, in center. Okay, now, number 5 is different. Why? Can we use this chart? Because the chart is all about the hypothesis. The chart is all about what segments are used to create this center. This center has already been created, and now it's showing you the conclusion. What type of center is it that is the same distance away from each of the vertices? In other words, what this means is I can draw a circle right around this, and that would be my center. So what kind of center is that? Circumcenter. I'm not sure if that's what you said or not. That's one of the benefits of a internet-based instruction, right? You can go center. Okay. What about number 7? Similar to number 5, this is actually the result. It's the consequence. What that means is that the distance from the center to this side and to this side and to this side, since they're perpendicular, those are the shortest distance, the distance from that point to those sides. In other words, it forms a circle on the inside, which makes it an in-center. All right. What about this last one?
Is none of the above an option?
It is not. This picture is showing you a bunch of junk, but the junk is consistent. It's just actually missing one little mark. Go by the chart. Use the hypothesis.
There are segment bisectors, circumcenter.
Very good. Those are perpendicular bisectors. They're perpendicular and they're through the midpoint. So it's the circumcenter. If in fact it's the circumcenter, what would be known about it? What would be the conclusion? That these lengths would all be the same. That's why they're in the picture. But they weren't marked that way. So you're right, this is the circumcenter. Because it's formed with perpendicular bisectors. How do you feel about the centers? Please give me an answer in the chat. 5, I think I have a strong grasp of them. I know which parts make what. I know what the result of each of them is. I know how to interpret it from a picture. And I even know the elements that make each part. I could sketch it. 3, with notes, I feel confident I can identify these, but it still takes some work. 1, there's just one center in a triangle. What are you making all this stuff up about other centers for? Okay, good. Good scores. Again, the expectation is that with the notes, you can make identifications and predictions about what's true about shapes like these. Okay. Now, move into triangle inequality theorem. If I give you 3 sticks of random sizes, can you put them end to end to make a triangle? Any 3 sticks, any side lengths, can you put them together to make a triangle by touching the ends together?
No.
No?
No.
Oh? Why not? You're right. I think intuitively we all feel like, sure, I could always make a triangle, but what if I gave you a length of 5 and a length of 3 and a length of 1,000? If you tried to put those together, what you'd end up with is this 1,000 stringing out and a little 5 on the end here and a little 3 on the end there, and it wouldn't make a triangle because those 2 pieces wouldn't reach, right? They wouldn't fall together and make the like teepee top that you need in a triangle. So instead, let me ask, if I give you a 5 and a 3, what length could this be? There's a bunch of answers, right? Somebody give me one length that would work.
Well, I think like 5 would work.
5 would work, sure. This one would stick really, right? It would end up looking like an isosceles triangle, which it would be, right? What else would work?
4.
4 would work. It's so interesting doing this with various classes. And I'm sure it's the way I present it, a little change in the way I say things or the sequencing of the words I use, but I always expect the same answers. If we knew that this 1,000 wouldn't work because the 3 and the 5 won't come together to kind of meet on top, what's the length of this that won't work? where it begins to be
9.
good. 9 won't work. It's too far, isn't it? Because 3 and 5 then won't reach to touch. They'll fall short of it. If this was 9, 5 would go to there, 3 would go to there, and you'd be short an inch. Would 8 work?
Yep.
Would it? If this is 8, my 5 and my 3 would actually together make a straight line. They wouldn't have a chance to bend up and make a triangle, right? So this is like a critical value, but it doesn't quite work. But what if I were to say like 7.9999999, whatever, repeating? Now I'd have these two things making a combined length of 8, which is too long to fit on a 7.999. So it would fit a really, really narrow obtuse triangle, but it would work. How did you get that number 8 though? Where'd that come from?
The sum of the two sides.
And does that make sense that you need these two sides to be bigger than the base so that they can't fall down flat? They've got to like fall into each other and make a little pitched roof.
Yeah.
Okay. So in other words, if we're looking for the side X, this part here has to be less than 5 and 3 together. X has to be less than 8. Agreed? Could it be 1?
No,
Good. Why not, Harrison?
because 3 plus 1 is less than 5.
Right. In other words, what if we then said, now we're getting so that this side is no longer the base. Now we're making 5 the base, and we've got this side being 3. What does this one have to be so that it makes a triangle? What can't it be?
It has to be, wait.
What makes it a straight line?
2.
2, right? If this is 2 and this is 3, then it falls down and makes a perfectly straight line. It's not. So we need to be a little bit bigger than 2 so that it sticks up and catches the other side. So this one has to be 2 is less than X. How do you think we got 2? We got our 8 by adding these two together, 5 and 3. How do you think we got the 2?
You subtract one side from the other.
Very good. Subtracting those gives you 2. And so what you guys have just done is you've identified the triangle inequality theorem through discovery. You've said, if a triangle is to exist, then the sum of the two smaller sides must be greater than the largest side. If a triangle is to exist, then the sum of the two smaller sides must be greater than the largest side. So, which are the two smaller sides here? So I need 8 plus 17 to be greater than 24. Does that work? 8 and 17 is 25. That is greater than 24. So we can say, yes, it is a triangle. What about this one? Which two sides should add together? 3 plus 3 is supposed to be greater than 7. 3 plus 3 is 6. Is that greater than 7? It's not. So I'm going to cross through this and say that 6 is not greater than 7. Therefore, no. Not a triangle. Which one should I add here? Sum of the two smaller sides. Smaller. Which are the smaller numbers here?
12 and 25.
Yep. And that has to be greater than the biggest one. In this case, 12 and 25 makes 37, which is greater than 35. That's true. So yes, it makes a triangle. Jump down here to number 5 for a moment. Which one should I add up here?
$28 and $22.
And those should be better than 50 or bigger than 50. But in this case, I get 50 is greater than 50. Does that work? Is that going to make a triangle for us? Nope, it's not greater. It's the same. In other words, it would make a straight line. It would not make a triangle. Any questions on this aspect of the triangle inequality theorem? There's 3 more parts to it. I'm going to leave these open. These will be your homework to complete these. Okay, next part is finding a range. What about the 2 sides are given? Let's find a third side. Give me a number that would work. Like, would 10 work? Because 10 plus 14 is bigger than 22. Agreed? So could I use 20? 20 plus 14 is bigger than 22. So I can use anywhere between 10 and 20. What's the smallest I could go? What would happen? What would you have to add to 14 so that it's not bigger than 22?
8.
8. So that's the smallest. If I go any less than that, or even including 8, it's not going to work, right? So I know that the 8 is the smallest we can go. We have to have x be bigger than 8. How did we get 8? Besides listening to Harrison.
Because 14 plus 8 equals 22.
Okay. Is there a different way to express that?
You could do 22 minus 14.
Yes.
Right?
Given the 2 numbers that we've got, let's do the subtraction. So in other words, we know that x has to be greater than the difference between these 2. Oh, but what if 22 is not the biggest one? Is it possible that 14 is the biggest one? No, because 22 is already bigger. But is it possible that our missing one is bigger than 22? Is it possible that it could be too big? Like if it was 100, would it work? It wouldn't. Why not? because 14 plus 21 wouldn't be bigger. So our upper end comes from the idea of, if these two are not the biggest ones, then we need their sum to be bigger than x, right? Their sum has to be bigger than the biggest side, which in this case would be 36. So as you can see, the range for these two is going to be trapped between the difference of the two given sides, 22 minus 14, and the sum of the two sides, 22 plus 14. So in this case, if we want to find a value of x for the missing side, it's trapped between 31 minus 28 and 31 plus 28. 31 minus 28 is 3. 31 plus 28 is 59. So number 11, if I want to find the range of possible values, I want x to be trapped between 11 minus 3 and 11 plus 3. 11 minus 3 is 8. 11 plus 3 is 14. Any questions on that? So the last piece is suggesting, now that you know that, would you be able to rattle off a list and decide if these pieces are all valuable? Would they make a triangle? Easiest way to do it would be to do the skill we just did. What's the range? So how do I find the range for these two of the third side? Well, same way, 27 minus 15 has to be less than x, which has to be less than 27 plus 15. So 12 has to be less than x, which is less than 42. So that's my rule for this problem. I need that to be greater than 12 but less than 42. Is 34 greater than 12 and less than 42? Sure is, that'll work. What about 12 feet? Is that going to work? No, because that would be equal to it. We need it to be greater than 12. 29 is between those two, so that works. 18 is between those two, so that works. 43, nope, that's too big. Any questions? You can finish up these four as part of your homework as well. Now, I know that this probably will dash your perspective of who I am as an educated man, but I grew up watching cartoons. And I used to watch cartoons about cavemen and dinosaurs. And talk about the worst cartoons, because that's not like historically accurate. Cavemen and dinosaurs didn't exist at the same time. But I can vividly remember pictures of like a cliff with a cave cut out of it and a little kind of porch deck he's got off the front. And he'd be sitting out there tending to his fire. And suddenly the caveman is approached by this huge Tyrannosaurus Rex. And his mouth opens up and there's like saliva dripping off his big teeth. And he's about to chomp the man. How does he save himself? Come on, you saw this too. What does he stick in the thing's mouth?
The fire.
Ooh, fire would be a brilliant solution. That's not the ones I saw. We weren't thinking that hard.
Well, if you're referencing the Flintstones, he'd get up, run in like midair for several seconds, and then speed away at several hundred miles per hour.
I like this speeding. But no, this is an aggressive move to protect himself. What does he do?
Put a stick in the mouth?
Yes. He picks up a stick or like this huge bone that he happens to have there, right? And he puts it inside the mouth, and this huge beast that's about to chomp down and goes, ah, 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 and he's trapped, right? He's got this stick holding open his mouth and he can't chomp anymore, and he goes off and he's whining, right? So this is what I picture when I think of this theorem. Because if the dinosaur's mouth is open with a huge hinged angle, then he has to put a really tall stick in. But if the dinosaur is just opening his mouth a little bit with a little small angle, you can put a little small stick in there. It doesn't need to be a big stick, doesn't it? So this is an extension of the triangle inequality theorem. It basically says that the angles of a triangle can be put in order by comparing the sides. In other words, the smallest angle is always opposite the smallest side. And the largest angle is always opposite the largest side. So for example, if this is my triangle, since the stick of size 7 is the smallest one here, I put a little s next to it. What's my mediumest size stick? 10. What's my largest size stick? And I guess with my largely Mill Valley audience, should I say tall, grande, and venti? No, okay. So once I've established these lengths, I can then list the angles from least to greatest. So if this side is smallest, then the angle that's not touching it would be the smallest. So from least to greatest, angle A is the smallest. What's my mediumest angle?
Angle C.
Very good. Opposite the mediumest side. And then my largest angle is the one opposite the largest side. So again, if I want to do this, I recommend you put the SMLs in there. I think they're helpful. So here's my smallest side. Here's my mediumest side. Here's my largest side, which means when I list the angles from least to greatest, I would go angle M first, medium, angle P, and angle N. And that would be ordered from least to greatest. Do be careful, because all they have to do is a little change to the wording, like on problem number 19, where it says order the measures from greatest to least. The process starts the same. I have small, medium, and large. But now I want to start with the biggest one. So angle C is the biggest, angle B is the mediumest, and angle D is the smallest. And of course, the converse of this works as well. The smallest side is always opposite the smallest angle. And the largest side is always opposite the largest angle. The difference here is, what did they do to make us work a little bit? They only gave us 2 of the angles, right? So we have to find the third. Well, that's okay. We know that 103 plus 42 plus F must equal 180 because it's a triangle. So 145 plus F equals 180. So F is 35 degrees. Now that I've done that, what's my smallest angle? What's my mediumest angle? What's my largest angle? So if I want to order the side lengths from least to greatest, I want the side that's opposite my 35 degrees. And notice that there's 2 sides that touch my 35 degrees, EF and DF. Those touch F. I want the one that's not touching F. That's what opposite means. So I'd say ED. My mediumest angle is over here, so the opposite side would be DF, and my largest side would be EF. Any questions? So again, if we want to apply it to another problem, they're giving us a couple of angles. We should find the third. So 31 plus 57 plus k equals 180. 88 plus k equals 180, so k is equal to 92. All right. That then lets me label small, medium, large. I'm trying to go least to greatest. So I want to find my smallest side. First identify my smallest angle, and then look for the side that's opposite it. If this is the jaw of the mouth, how big does this stick have to be? In this case, it would be KL. And then the mediumest would be opposite this angle, so JK. And then opposite this would be JL. Any questions on how to stop a dinosaur from charging you? Okay. Last page. So at the top of this page, I've got kind of like what's a bonus problem. Big ideas would never give you this problem. They don't think you're capable of it. I do. I've seen this in books before, and I love this problem. The question's the same. I'm giving you the angles, and you're supposed to list the sides, this time in descending order from greatest to least. But there's something about this problem that makes it trickier. What is it?
Triangles are not congruent.
Okay. And it would make it easier if the triangles were congruent because what?
Then the same angle measures would be representative of the same side lengths.
Ah, right. So in this case, we don't have that. And what's true about that BD? Is it a big one or a little one? In other words, is it opposite a big angle or is it opposite a little angle?
Both.
Both. Dope. That's the quandary, isn't it? Is that one supposed to be big because it's opposite 100, or is it supposed to be little because it's opposite 30? So here's my solution for this. Let's see, I'm going to pick somebody out of the window here. Lucy, would you please pick for me a number between 5 and 10? Any number between 5 and 10. Let's keep it an integer. Let's not get crazy.
Oh, 7.
7. No, not that number. Just kidding. Sorry. 7 is fine. So what I'm going to do is I'm going to put a 7 right here. I'm going to pretend that BD is 7. Is it really 7? No. I mean, it could be. I have no idea. But the reason I do this is to get a relative understanding of the impact. So now I'm going to block off this triangle over here and just treat this as a single triangle. The 7 is opposite 100 degrees. That means that the side marked as 7 is what? The biggest, middlest, or smallest side?
The biggest side?
It's the biggest side, right? Because it's opposite the biggest angle. That means that if I choose the side opposite the next bigger angle, in other words, a little bit smaller than 7, this number has to be a little bit smaller than 7. I don't know what the actual value is, but I'm going to put a number in there that is a little bit smaller than 7, 6. And relatively, I'm showing the sequence of small, medium, large, right? What about the side opposite 30? What do I know about that?
It's smaller than 6.
Yeah, it's smaller than either of the other two. It has to be the smallest of this triangle. Is it 5.93? Is it 4.87? Is it 1.7? I don't know. I'm just going to mark it with a 5 because it's an easy number to work with. And again, I'm not really demonstrating these are the lengths, but I'm saying that this is the smallest, this is the mediumest, this is the largest within this triangle. And I could have done it with SMLs. The reason I chose to use numbers is because now it carries forth to this other side as well. On this triangle, remember this was 7, and that's opposite 30 degrees, the smallest angle. So if I move over here and say this is the next smallest angle, opposite this should be how related to 7? Should it be bigger or smaller? Seven's the smallest angle, so this one should be a little bit bigger, shouldn't it? What's a number a little bit bigger than 7? How about 8? And the side opposite 80, the largest angle, should be the biggest among this triangle. So what could I put in as here as a number, knowing that it's bigger than 7 and 8? Could I have put 10? Sure. Could I have put 30? Well, it violates our triangle inequality theorem, but it would still give me the sequencing. All I care about is the sides in descending order. Descending means top down. So what's the largest side I was given here? That's 9. That's the biggest number I've got out here. Working my way down, what's the next biggest side? 8. BC. Next, the shared side, BD. And then 6, so AD. And the smallest side is AB. With that little trick of picking some number for the middle, I think this problem is pretty easy. Without that trick, it's kind of confusing. But all we're saying is that it has to be the smallest side in this triangle and the largest side in this triangle. Any questions on that bonus problem? Okay, last piece. This talks about the Hinge Theorem. And the idea behind the Hinge Theorem is if I take, let's go with this 2. If I take 2 sides and make an angle, let's say I make that angle, and I'm forcing them to have some angle here. By side, angle, side, does that lock in the triangle, letting me know that there exists exactly one triangle like that? So that if I chose another pair, and I chose it so this purple is the same size as that blue, and this maroon, what color is that? Plum, is the same size as that red, then these 2 angles would be congruent. Excuse me, and I chose the angles to be congruent. These 2 triangles formed would be congruent. You okay with that? And if I were to take this angle and start to open it, in other words, I start to increase this angle, the blue side wouldn't change and the red side wouldn't change, but what would happen over here? It expands, doesn't it? So what the Hinge theorem says is if you've got a side and another side, and you compare just the angle in between, like hinges on a door, right? Just this swinging angle in between. If that angle in between is bigger than another one with the same sets of sides, then the facing side must be bigger as well. So in this picture, for example, it shows that ED and BA are both the same size. And then it shows that AC and DF are the same size. And if you know that angle A, the measure of angle A, is bigger than the measure of angle D. In other words, you know that this one is something like 80 degrees and this one is only like 60 degrees. What can you say in response to that? This one's been opened up more. So doesn't that mean that BC has to be greater than EF? If the hinge swings open, opening across the end is also open. And the same works the other way. Oops. So if you know that, for example, BC is bigger than EF, if this is bigger than this and these side pairs are the same, then this angle has to be smaller. Angle A, measure, must be bigger than the measure of angle D. How does that work in our pictures down here? Well, I can see that I've got a 9 and a 9. And I can see that I've got a 15 and a 15. So I've got these hinges, right? That's what I'm talking about. And this hinge swings 79, and this hinge only swings 74. So which leg is bigger, KL or PM?
Well, if the angle is bigger, then wouldn't KL be larger?
Exactly right. Since this angle is bigger, it's pushing it open more. So KL is bigger than PM. We don't know by how much. It's not a linear relationship, but we do know that it's going to be bigger. Same thing here with number 2. I've got 24 here and 24 here. It only works if I can find another side length the same. Look at this. I've got reflexive. My old buddy reflexive. So I've got the 2 hinges. One is hinged at 65 degrees, and the other is open to 59 degrees. So how do AD and BC compare? Is AD bigger than BC, or is AD less than BC? AD is facing 59, BC is facing 65. 59 is less, so AD must be less. That's all we're doing. Okay, ladies and gentlemen, your homework is to finish the few problems that I left you. I think it's about 10 or 11. Please finish those problems out. That is your only homework for the break. If you haven't done the tests, you do need to do the tests, the unit tests for this class in order to pass. If you want to do them over break, like for example, the Unit 4 test that you may not have completed yet, you need to ask me to open it up for you again because it's closed down at this point. So if you want to stay after right now and ask me to open it up for you for the break, I'll happily do that for you. If you have done all you need to do and you're ready to just shut down your screen because you've been cranking through this homework and you're just going to like load it up real quick and then be done and have a week off, you may do that as well. Have a great break. I hope you come back refreshed, and I'll see you when we get back.
Thank you.